that the second time. Okay, now we've got a whole bunch of people here. Anyway, if a sound source is moving toward a listener, or if the listener is moving toward the source, the listener will hear a higher frequency. And if a sound source is moving away from a listener, or if the listener is moving away from the source, the listener will hear a lower frequency. So that's what it boils down to. Now, the formula is not going to be particularly intuitive, but we'll manage to learn how to deal with it. And there's a couple of different ways of writing it. One way is this way, where you've got V plus V sub L. V is the speed of sound. This would be the speed of the listener. You have that on top. And then on the bottom, you have the speed of sound plus or minus the speed of the source. And I don't expect you to be that comfortable with just where Y is one of them in the numerator and the other denominator. I'll have to show you the derivations for those in a separate video, or you might be able to track it down somewhere. I'm surprised it isn't in your textbook, because I remember using a textbook that it was in, but it's been a while anyway. Okay, but how to use this? Oh, and by the way, if you multiply top and bottom of this by 1 over the speed of sound, 1 over V, the formula turns into this. And this is a little more intuitive because this is the part that shows what effect it's going to have. And it's how fast the listener is moving compared to the speed of sound, or how fast the source is moving compared to the speed of sound. And that may be a little more intuitive, but I'll show you how to use this formula. Sometimes we'll have both the listener and the source moving, but there are ways to learn how to deal with this. And the two important things for learning how to deal with this are keeping these in mind. If the source and the listener are moving toward each other, or source here, listener here, and the listener is moving in that direction, the listener will hear a higher frequency. If the listener's here and the source is moving toward the listener, then the listener will hear a higher frequency. So anyway, let's try some example problems and see how this works. I've got this formula here. We start with a person on a railroad car blows a trumpet sounding at 440.0 hertz. And believe it or not, back in the 1800s, when Christian Doppler developed this formula, this was how they demonstrated it. They had a person on a railroad car blowing a trumpet. They had someone with perfect pitch standing alongside the track as the train was moving toward them or moving away from them, and they would say what pitch they heard. And now it may not have been a perfect note, like maybe they heard instead of an A, maybe they heard a B flat or a B or something like that, but they'd be able to say that it was definitely not a concert A. This is an A on the musical scale, by the way, 440 hertz is. So they were able to do that, and it sounds very quaint. They probably wore top hats and ties or something like that. I don't know. Anyway, nowadays everybody be out in jeans and t-shirts. So, all right. Anyway, the car is moving toward a wall at 20.0 meters per second. Calculate the frequency of the sound as received at the wall. So for part A, we're imagining that we have a sound source moving toward the wall at 20 meters per second. And we're almost always going to use V is equal to 344 meters per second, unless told otherwise. Actually, one of the examples we're doing has to do with sonar sound in water. So that definitely won't go at 344 meters per second, but that's what we'll use. So for part A, we have a source moving toward a listener. So and we have a listener at rest. Okay, so in that case, we'll have a moving source. So we'll use something on the bottom. The listener is at rest, so this is 0. And on top, we'll just have, if we use this formula, we'll have just a 1 on top. And so the frequency heard by the listener, which could be thought of as maybe a person standing there at the wall, or maybe the wall itself, if it's an animate object. The listener is at rest, so this term is 0, and we'll just have a 1 on top. And then on the bottom, we'll have 1 plus or minus the speed of the source divided by the speed of sound. And we multiply that by the frequency generated at the source, which is the 440 hertz. Okay, now, if the source is moving toward the listener, will the listener hear a higher frequency or a lower frequency? They'll hear a higher frequency when things are moving together. So in this expression, what do I do to this to make the things in the parentheses something bigger than 1? Well, I've got a 1 on top. I'd have to be dividing by something less than 1, which is what we get when we have a minus sign down there. So that's the version of the formula that I'll use. And that's how I do it every time. I look at it and think, okay, higher frequency or lower frequency. If it's on the bottom of the fraction, to make it a higher frequency, you need a minus sign down there. And so we'll have 1 over 1 minus the speed of the source over the speed of sound times the frequency of the source. So let's go ahead and plug in the numbers and see what we get. 1 minus the train's going, or the car, railroad car, and a train, it's 20 meters per second. So 20.0 meters per second divided by 344 meters per second times the frequency of the sound, 440.0 hertz. Then we'll get a different frequency. The frequency heard by the listener is, oh, where did I put it? Buried it. And I get 461 hertz. And let's see, I only have 3 sig figs, so I'll just call it that. Okay, so that's the frequency that's received at the wall. The second part asks for the frequency of the reflected sound arriving back at the source. So now the wall is acting as the source of the sound, because we're talking about the echo here. And the listener in this case is somebody who's on the train. So for part B, we'll have the source at rest. At rest. And let's see. Listener on the train. And maybe these things are kind of confusing to try and get used to, but the interesting problems all kind of do that. Listener moving toward the source. At, again, 20.0 meters per second. Okay, so if the source is at rest, this Vs over V in the formula is 0, because Vs is 0. So we just have a 1 on the bottom, and on top we'll have 1 plus VL over V, or 1 plus or minus VL over V. And so generically, the formula looks like the frequency heard by the listener is going to be 1 plus or minus V sub L over V divided by just 1, and then we multiply that by the frequency of the source. Now we have the listener moving toward the source. Will they hear a higher frequency or a lower frequency? They'll hear a higher frequency. And so the way to get a higher frequency when the listener is the one moving is to have the plus sign up here. So that's all I have to do. Now, the trick here is the frequency that's generated by the source, which is the wall, is that 461 hertz that the wall received coming from the train moving toward it. So that's part that's kind of tricky to use. But anyway, we'll have 1 plus 20.0 meters per second over 440.0. Yeah, we have, let's see, 4 sigs everywhere except on that thing. But that's a hertz, or a hertz is a per second, but we're multiplying by 461 hertz. Oh, yeah, what am I doing? Good grief. On the bottom of that thing, I've got the speed of sound, which is 344 meters per second. The way I caught that was by looking at my units, and I knew that inside these parentheses had to be dimensionless. And so I had something there with units of hertz, which wouldn't divide out with meters per second. So that's why I write down units everywhere, because they catch mistakes. Oh, shoot. Had a wrong sign in my, or a wrong thingamajiggy. I had 1 times 20 over that instead of 1 plus. Okay, and I get 488 hertz. So I'm going to do a quick calculation here just to figure out where that would be on the musical scale. And don't worry about the details of that. Oh, okay. Well, where it would be on musical scale is bouncing back to the listener on the train. They'd be hearing about a B flat note. So that'd be about the frequency of that. So it doesn't matter. But there's our first example anyway. So let's try some more. Okay. This one may seem a bit confusing because you have both the source of sound and the listener moving in the same direction. In fact, they're both moving at the same speed. So let's see what happens in this case. They're moving at a speed of 100 miles per hour. We're given the speed of sound in air as 1,100 feet per second. So if we convert this into feet per second, because we've got those ratios of speeds in the formula, the units will divide out. And as long as we have the same units for both. So 100 miles per hour, and we're not going to have a lot of sig figs on here. So it's kind of ridiculous that that happens to be the case, but let's see, times, actually, we may not even need to do anything unit-wise on this. Yeah, we might not have to, but I'll go ahead and do it anyway. Anyway, 5,280 feet per mile times 1 hour over 3,600 seconds. And 100 miles an hour is about 147 feet per second. Okay, now here's what the formula looks like. Come back to that thing. Okay, the VL's on top and the VS on the bottom. So the frequency heard by the listener, which in this case is the shift in frequency heard by the speeder A, is going to be 1 plus or minus. I think I said the VLs were on top. What a memory I've got. Yes, they are. VL over V, just plain V. And on the bottom is 1 plus or minus VS over V times the frequency that's generated by the source. Okay, I'm going to do this just the same as, well, here's what I do for determining the sign on top. Okay, I imagine, okay, the listener is moving to the right, the source is to the left. Would the listener hear a higher frequency or a lower frequency? Well, if the source is here and the listener is here and they're moving in that direction, if the source was at rest, they'd hear a lower frequency. What sign would I put on top for them to perceive a lower frequency? I'd have a minus sign on top. So that tells me what sign to put on top. I pretend for a moment that the source is not moving. So I'd have 1 minus V sub L over V. Then I think, okay, now let's imagine that the listener is not moving, but the source is. Okay, so the source is listeners here, source is to their left, and the source is moving to the right toward the listener. They'd hear a higher frequency. You'd have to have a, in the bottom of the fraction to get a higher frequency, you'd have to have a minus sign down there. So you'd have 1 minus V sub S over V. Okay, now recognize that V sub L is equal to V sub S. They're both moving at 147 feet per second. Whoops, I still have to have the frequency of the source here. Well, what's that going to do to the sound heard by the source? That means 1 minus V sub L over V will equal 1 minus V sub S over V because they're going at the same frequency. So this ratio is just 1. And that means the frequency heard by the listener is the same as the frequency generated by the source. And that's the case when they're both going at the same speed. So this can be kind of mind-boggling to try and wrap your head around, but see if you can work through that. When you've got both source and listener moving to figure out the signs, start by pretending one of them's at rest and think, okay, which direction is the listener going relative to the source? And that will let you pick the sign for the listener part. Then imagine the listener is at rest and the source is moving. Is the source moving toward the listener or away from the listener? and choose your sign accordingly. So let's try another one. Okay. A French submarine and a U.S. submarine move head-on during NATO maneuvers in motionless water in the North Atlantic. The French sub moves at 50 kilometers per hour, the U.S. sub at 70 kilometers per hour. The French sub sends out a sonar signal at 1011 hertz. Sonar waves travel at 5,470 kilometers per hour. What is the signal's frequency as detected by the U.S. sub? And what frequency is detected by the French sub in the signal reflected to it by the U.S. sub? All right. Now, remember, in that formula we're going to be dealing with here, we'll have the frequency heard by the listener is equal to, I've got it on another sheet of paper here, it's 1 plus V sub L over V divided by, 1 plus or minus, 1 plus or minus V sub S over V, and it's times the frequency generated by the source. Okay, because we've got a ratio of speeds here, as long as the speeds are measured in the same units, we don't have to convert them to meters per second or anything. And we've got the speed of the French sub in kilometers per hour, US sub in kilometers per hour, and sonar waves in kilometers per hour. So everything's in kilometers per hour. I don't have to do any unit conversion there. I do, however, have to think about the plus and minus parts here. So we've got velocity of the source. Whoops. No, this is just the source. This is the listener. And this is the French sub. This is the US sub. And by the way, they're on the same side in NATO. That stands for North Atlantic Treaty Organization, something that formed after World War II. And right now, there's a move afoot to gradually, or at some point in the future, add Ukraine to that organization if it still exists as an independent country. Anyway, so here's what we have. We have both of these things heading toward each other. But for purposes of figuring out the signs, I'll deal with one at a time and pretend that the other one's at rest. So let's see, we'll have, let's do the denominator first this time, okay? We've got the source of sound moving in that direction. That's toward the listener, okay? So what sign would we use on here to produce a higher frequency? When the source is moving toward the listener, if the listener wasn't moving, the listener would hear a higher frequency. What do we do to the bottom to get a higher frequency? We have to use the minus sign to make this thing less than 1. So on the bottom, we'd have a minus sign. Now we'll consider the top. We've got a listener that's moving in this direction. That's toward the source. What sign do we use? The source would hear a higher frequency coming from the listener, if that, or the listener would hear a higher frequency coming from the source, if that was the case. To get a higher frequency, we need a plus sign on top. So we need 1 plus VL over VS. All right. And let's hang on to that because we actually use it twice on this problem. So the frequency of, then multiply that by the frequency of the source. Frequency of the source is 1011 hertz. The French sub is moving at 50 kilometers per hour, 50.0. So we've got 3 sig figs on that. US sub at 70.0 kilometers per hour. And then the speed of sound in water is that. So I think I can just plug in the numbers here. the frequency heard by the listener in this case is 1 plus speed of the listener over speed of the, whoops, that's just supposed to be the speed of sound there. Let's see, listener is the US sub in this case, so 70.0 divided by 5470. And down here we'll have 1 minus the speed of the source, which is 50.0. Oh, this is kilometers per hour. And then on the bottom, kilometers per hour. And again, the speed of the sound. And then multiply all of that by 1011 hertz. And dimensionless quantity here, dimensionless quantity here, should be good. And all of that times, and I get 1033 hertz for the frequency that's received at the US sub there. Now for something like this, there'd be some kind of some instrument on the US sub, or the French, yeah, the US sub, that would receive that, although they might not know the frequency of the signal that was sent out from the French sub. So, although I would guess that the, I don't know, they probably knew. They probably keep track of the frequencies sent out by sonar signals. Although my guess is if it was actually a sub on the other side that they wouldn't know the frequency. They might have some way of varying the frequency of their sonar signals. So people wouldn't know, couldn't immediately determine from just receiving a signal how fast the other ship was going. However, the whole point of this is the French sub would send a signal out to the US sub, which would bounce off the US sub, and they'd listen for the echo. And knowing their own speed and knowing the speed or the frequency of the echo that comes back, they could figure out how fast the US sub is moving away. And if they did something like just sent out a single ping, they could also determine how far away the US sub is from the round trip time. So lots of stuff. Now for part B, we go and what frequency is detected by the French sub in the signal reflected to it by the US sub. Well, now the frequency of the source is going to be this 1033 hertz. We still have the source and the listener moving together, but now the source is going to be the French sub. So V source is, or no, now the source is going to be the US sub because it's the signal bouncing off the US sub. So that'll be 70.0 kilometers per hour. The listener is the French sub, which is moving at 50 kilometers per hour. We already figured out that when we have both source and listener moving toward each other, this is the formula to use. So we can use that again, but we have to swap where the things are. So we'll have the frequency heard by the listener this time is going to be 1 plus velocity of the listener was 50 kilometers per hour. over the 5,470 kilometers per hour. And then on the bottom, we'll have the 1 minus, but now we've got the source is the one that's moving at 70 kilometers an hour. So try these problems out on your own after class, after having seen them, and see if you can correctly apply the formula when you're not just watching me do it. So anyway, times 1,033 hertz. And let's see if I can punch it into my calculator correctly. That's the big challenge. That looks good. And the signal it bounces back is 1,056 hertz. So they sent out a signal of frequency 1,011 hertz, received back something at 1,056 hertz, and something on the French sub would probably measure the frequency difference and determine the speed of the US sub from that, and perhaps the distance if they did something to time the round trip time. By the way, this is what, if you ever watch a baseball game and they're measuring the speed of the pitches, watch one on TV, what they measure it with is a radar gun that sends out electromagnetic waves, and when they bounce off the incoming baseball, they can measure the speed of the baseball from the Doppler shift. It's the same thing the State Patrol uses in measuring the speed of cars that are going by on the way. I don't know if they have the ability to do it when the State Patrol car is simultaneously moving or not, but it would be easy enough to build in to the radar gun on a State Patrol car the some kind of a tie-in with the speed of the car, and to be able to determine the speed of cars that are moving relative to it. Whether they do that or not, I don't know. Most of the time when you see them, they're sitting there using a handheld radar gun aimed at cars and working it that way. Okay, true story. While walking to school one day, a physics instructor hears a goose honking as it flies overhead. He notices that the honk drops in pitch by a major second. That's a musical interval equal to 2 half steps as the goose flies overhead. Can the speed of the goose be determined from this information? And if so, what is the speed of the goose? Okay, well, you need a little bit more background. This is a Doppler effect problem, but in the music scale in use in Western countries, for each half step higher on the scale, the frequency increases by a factor of the 12th root of 2. There are 12 half steps in an octave, and when you multiply those things together, well, I'll write it down for you so you can kind of see what's going on with that. Well, there went my calculator. Let's see. Okay, if you write down a musical scale like the chromatic scale, you go C, C sharp, D, D sharp. And by the way, this could also be written as D flat. This could be written as E flat. And then you get to E. There's only a half step between E and F. So you keep going up here. I'm just going to use all sharps. G, G sharp, A sharp, B, and then there's only a half step between B and C. And if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You get up to there. Well, the frequency of a C is going to be some number, but the frequency of the C sharp is going to equal the frequency of the C times the 12th root of 2. The frequency of a D is going to equal the frequency of a C sharp times the 12th root of 2. But the frequency of a C sharp was already the frequency of the C times the 12th root of 2. And that'll be the frequency of a C times the 12th root of 2. And so far, this is just the frequency of the C sharp, but then you multiply the 12th root of 2 again. And so it's the frequency of a C times the 12th root of 2 to the second power. As you go up the scale, you can write everything in the scale in terms of the frequency of C times the 12th root of 2, except here it's the 12th root of 2 to the first power, 12th root of 2 to the second power, 12th root of 2 to the third power. And when you get up here, if I call this, maybe this is C1 down here, and this is C2 up here, an octave higher, the frequency of C2 would equal the frequency of C1 times the 12th root of 2 to the 12th power. Well, you can rewrite the 12th root of 2 as 2 to the 1/12th. 2 to the 1/12th to the 12th power is 2 to the 1. It doubles the frequency. So that's something that happens. But in this case, we're not going up a whole octave. We're just going to be going a major second, which is 2 half steps on the scale. It could be a C to a D, or a C sharp to a D sharp, or an E to an F sharp, or an F to a G, something like that. People who have perfect pitch can immediately tell exactly what note in the scale it happens to be. People with perfect pitch who've practiced it are amazing. When I was a student, I went to North Seattle Community College for a while, and I sang in the jazz choir. And the director of that was an amazing piano player, jazz piano player, but he had perfect pitch. And we would test it. We'd have 2 or 3 of us would strike notes simultaneously on the piano somewhere, and he could name every one of the notes, despite whatever distractions were going on. So that was kind of amazing. He didn't have to see us do it either. He could just listen and get it. But anyway, we're going up. The frequency is going to be a major second. That means the frequency approaching is going to equal, or the frequency approaching was a higher frequency by a musical major second. And I'll write it F sub RE. It'll be times the 12th root of 2 times the 12th root of 2 again, because that's what makes it a major second. And the way it sounded was, as it comes in, it was going like honk, 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 honk. That's a drop of a major second there. And so that's what was going on. Well, the frequency approaching, we had the goose moving toward us. So let's use our formula wherever I put it. Let's see. There's the formula. Let's use this and apply it to this particular problem. So the frequency that I heard as the goose was approaching would have been We've got a 1 plus or minus on top and a 1 plus or minus at the bottom. I would be the object at rest in this case. And then we can figure out the frequency of the goose from, no, maybe we can't. I don't think we can actually figure out the frequency of the goose, but we don't need it. So that's okay. Okay, what have we got? VL over V. Well, the listener is at rest. So this would be 0 over V, the speed of sound. And then on the bottom is the speed of the source. So I'd have 1 plus or minus V sub S over V. And that would be the frequency of the goose. The frequency receding, oh, what sign will we use? I heard the goose was approaching me. I would hear a higher frequency. So what I do to the bottom to get a higher frequency is to use the minus sign down there. So I would have 1 on top because the listener was not moving. And on the bottom, I would have 1 minus the velocity of the source, which is the goose, times V times whatever the frequency of the goose happened to be. When it was receding, F sub RE, again, the numerator is still just 1 because the listener, me, was not moving. So we just have a 1 on top, but a lower frequency heard. What I do to the bottom, the lower frequency, is a plus sign. So I would have 1 plus the velocity of the source over the speed of sound. Excuse me. I've come down with a cold. Anyway, I've got, that's what I happen to have. Now, earlier, I figured out this thing. This ends up being if I take the ratio of the frequency of approach and divide it by the frequency receding, what that's actually going to equal is the 12th root of 2 squared. So 2 to the 1/12th squared, which is 2 to the 1/6. So I can take the ratio of these two expressions and what I would have is this on top and this on bottom. So 1 over 1 minus V sub S over V divided by 1 over 1 plus V sub S over V. And that ratio, actually, I can simplify it. If I invert and multiply, I'll have 1 plus V sub S over V on top, and I'll have 1 minus V sub S over V on the bottom. And that will equal 2 to the 1/6. So now all I have to do is solve for V sub S. And I think I'd multiply out from underneath by that bottom thing. And I'll have 1 plus V sub S over V equals 2 to the 1/6 times 1 minus V sub S over V. Let's see. Distribute that 2 to the 1/6 through there, 2 to the 1/6 minus 2 to the 1/6 times V sub S over V. Let's see. Bring that across here and subtract both sides by 1. And I'll have V sub S over V plus 2 to the 1/6 times V sub S over V. I think that's right. Is equal to 2 to the 1/6 minus 1. That's right. Okay, and then multiply both sides by V. And I would, on the left side, what I'd have left is v sub s plus 2 to the 1/6 v sub s, which is equal to v sub s times 1 plus 2 to the 1/6. And on the right side, that's still going to equal 2 to the 1/6 minus 1. Whoops. How about this? And what I end up with is the speed of the source, which is the speed of the goose, is equal to, oh, no, this was just plain v, not v sub s. Okay, because I multiplied out from under, that's the speed of sound is what it happens to be. So v sub s will equal, oh, no, that was v sub s because that was still the left side. This is the right side, just plain v. So it'll equal v times 2 to the 1/6 minus 1 divided by, actually 2 to the 1/6 plus 1 on the bottom. Whoops, times that. There we go. And let's figure out how fast the goose is going. I mentioned in here that somewhere, temperature on the day was close to 0 degrees Celsius. It was actually just about this same time of winter quarter, so the third week of January. I wrote this problem the year that it happened, which was it would have been either winter of 1994 or 1995 when the first, I don't know, 18 months we lived in Moses Lake or so, we lived out on the base, and I would just walk along Patton Boulevard to get to work. People would often, who worked at the college, would often stop and ask me if I needed a ride, and I was just getting exercise out walking, but that's okay. Anyway, so I'll take my 332 meters per second, multiply by 2 caret 1 divided by 6 minus 1. And divide by 2 caret 1/6 plus 1. And I get about, let's see, how many significant figures can I put on here? If I keep 2 significant figures, I'd count myself as lucky. I get around 19 meters per second is what I get for it. Well, let's see. I multiply that by let's see, 90 miles an hour divided by 40 meters per second. Those two are about equal. I get about 43 miles per hour. And that's actually in the range of what Canadian geese can fly at. That's what it was that flew overhead. I would have estimated that because I would have thought the goose was going a bit faster than the average car speed on Patton Boulevard, where the speed limit's 35 miles an hour, but students late to class may be driving faster than that. So that's in the neighborhood or in the range of possibilities. So that was actually a doable calculation. And so there we are for Doppler effect problems. I'll see if I can do some careful sketches and do a derivation of that for you so you can see just where this particular equation comes from. And what you do is you first say that the source is at rest and calculate the version that just has the part in the numerator and then reverse the thing and work toward that. But that's enough for today. Tomorrow, I'm actually going to be starting on gravitation. So we'll switch to whatever chapter gravitation is, which I think may be 13, but I'm not sure. But a new topic. And next week, we'll be able to do a gravitation lab. And for that, I think one of the gravitation labs that we do is has to do with the simulation of the Galilean moons orbiting around Jupiter. And from that, you can figure out the mass of Jupiter. So we'll see how that goes. All right, but we'll stop recording here and end the recording.